Okay, so first of all, let me welcome you to the NPTEL live session. This is our first session. Uh, the course is Advanced Foundation Engineering, you all know. So, my name is sinjandebnath. I am a research scholar in the Department of Civil Engineering at IIT Kharagpur. And every Tuesday, I'm going to conduct a session from 6 p.m. to 8 p.m. And you are all advised to attend these sessions so that you can clear all your concepts and you will be able to solve the assignments very easily if you follow this session. Okay, so you are advised to attend all the sessions. So in today's session, I am going to solve several problems related to shallow foundations. So first of all, let me just discuss a brief about the foundation. So what are foundations actually? So foundations is the lowest part of a structure, that is it is a substructure that uh, transfers all the load from the superstructure to the ground, to the soil underneath. So there are we all know there are two types of foundation. One is shallow, another one is deep. So in case of shallow foundation, the embedment depth, that is the depth of the foundation, that is the depth of the foundation is could be equal to or less than that of its breadth. While in case of deep foundation, the embedment depth is always greater than the breadth of the foundation. So there are several types of shallow foundation like strip footing, spread footing, combined and raft. I will show you the pictures. And in case of deep foundation, there are pile foundation, caisson foundation, drilled shaft foundation, all these are there. So here are some pictures of shallow foundations. This one is the strip footing. You see, it is supporting a wall. The length, this is the length. It is very long compared to its breadth. And this is the strap footing. This one is the combined footing. This one is the mat foundation. This one is the isolated footing. All these are shallow foundations.
Sorry to interrupt you, sir, but we can't see the foundations you are talking about.
Can't you see the slides?
Yes, sir.
One
Please
minute.
change your slide.
Okay. Can you see now?
Yes, thank you, sir.
So these. One. So these are all the types of foundations. Okay. All these are shallow foundations. You will observe here that the depth. You see, these are all the depth. All the depth of the these are all the depths. You see, the depths are much lower, much lesser than its breadth. This is the breadth. You see, the breadth in all the cases, the breadth is much greater than its length. All these are shallow foundations. So we will discuss about shallow foundations in this session, in today's session. So the main two criteria for designing the shallow foundations, one is shear failure criterion, another is settlement criterion. So basically what it means, the load that is coming from the superstructure, that is a superstructural load which is coming from the building, it should not cause any shear failure in the soil, okay, in the soil layer. And in case of settlement criterion, the load that is coming from the building should not cause any undesirable settlement. Suppose it should not cause any undesirable settlement in the soil. We must take care both the things. Now let's come to the problem. So this is the first problem. A strip footing of width 3 meter is founded at a depth of 2 meter below the ground surface in a C5 soil. So first let me draw the footing. This one is the footing. The width is 3 meter. It is founded at a depth of 2 meter below the ground surface. Suppose this is the ground surface and the depth of this footing is 2 meter. This is a C5 soil. Okay. The cohesion is 30 kPa and the angle of shearing resistance, that is the phi, is 35 degrees. And so the question is, find the net shape bearing capacity of the foundation. Net shape means QNS. Okay. So we need to find out the QNS. But there are two conditions. We need to find out the net shape bearing capacity of the foundation if the location of the groundwater table is 1.25 meter below the ground level. So first of all, we are going to solve the first part, that is the 1A. So we are going to solve the problem 1A first. When the groundwater table is below 1.25 meter below the ground surface. So suppose the depth of the foundation is 2 meter and the groundwater level, suppose this one is the groundwater level, it is at 1.25 meter below the ground level. This one is the first problem. So in the first problem, that is in 1A, the groundwater table is 1.25 meter below the ground level. So we need to find out the net shape bearing capacity of the foundation. So first of all, we need to find out the effective surcharge at depth df. So what is the effective surcharge over here? So effective surcharge, suppose let me denote it by q. Let me denote it by q. Q is, so it is equal to dw gamma, that is gamma means this particular the weight of this layer. It is written over here. The unit weight of soil above the groundwater table is 17.5 kilometer meter. That is this is the unit weight of soil above the groundwater table, means over here. So the unit weight of this part is 17.5 kilonewton per meter cube, and the saturated unit weight of soil, that is the gamma sat. Gamma sat is 18.5 kilonewton per meter cube. Okay, so we need to find out the effective surcharge at this point, that is at depth df. So what will be? So it will be like the depth of this is the depth of the groundwater table, that is dw. This one is the dw. So dw into gamma, this is gamma, plus this one. This for this phase we must consider the submerged unit weight. Okay, for this phase we must consider the submerged unit weight. So what is the the depth of this part? This one is total df. Okay, and this one is total, this one is dw. So this one, only this portion will be df minus dw. And the unit weight, what is the unit weight? Unit weight is the submerged unit weight, that is this. So now what is the submerged unit weight of soil? That is submerged unit weight means gamma sat minus gamma W. Now gamma means gamma sat minus gamma W. So what was gamma sat? Gamma sat was 18.5 kilonewton per meter cube. It was 18.5 minus what is the unit weight of water? It is 9.81. Okay. So what is 18.5 minus 19.81? It is around 8.69, I believe. 8.69 kilonewton per meter cube. Please let me know if I do any calculation mistake. Okay. Please let me know. So gamma submerged is 8.69. So what is the effective surcharge at the depth df? So what is the effective surcharge? Q equal to dw gamma plus df minus dw into gamma submerged. The depth dw is equal to 1.25. The unit weight of this part, this portion, is 17.5 above the groundwater table. So 17.5 plus this portion df minus dw. What is df minus dw? Df is 2 meter, depth of 2 meter. So it is 2 meter minus dw is 1.25 and gamma submerged is 8.69. So this one comes to be you guys also calculate. I think it is 28.39 kilonewton per meter square. This one comes to be 28.39 kilonewton per meter square. Now what is our phi? Our phi is 35 degree. So for phi is equal to 35 degree, and we need to use the Terzaghi bearing capacity theory. Okay, or use the general shear failure theory of Terzaghi. So we need to consider that chart of Terzaghi bearing capacity factors. And if
Sorry to interrupt you, sir.
Okay, tell.
So we can't see what are you writing.
Uh, can you see this slide?
And just the question side. Oh,
You are okay. After can you see what I have written after the question, after the question slide?
just diagram and few things.
Okay, what are you seeing right now?
Uh, the diagram has written and DFC's value, 5 values, QNS values. You could write question mark. बस
Okay,
उतना ही.
okay, 1 minute.
Yeah, now we are able to see.
Can you see now?
Yeah, sir, can you please just repeat the first slide
Yes,
because you
yes,
write
yes.
many things there.
Okay, okay, 1 minute. Let me just check. Okay, so you okay. So you
Yeah,
see,
we can.
uh,
Yeah, we are able now.
shall I explain all the things once again?
Yes, sure,
Okay,
sir, please.
okay. So okay. So you see, what is the question? A strip footing of width 3 meter. This is the B value. This is the B. Okay. See, this is the B 3 meter is founded at a depth of 2 meter. This one is DF. This one is B. This one is DF. That is the depth of the foundation. Below the ground surface in a C5 soil, deposit having cohesion is equal to 30 kPa. So this is the cohesion I have written over here, and angle of shearing resistance phi equal to 35 degrees. I have written the
So
value
can
of
you explain the C5 soil? means.
C5 soil means it has both cohesion and that angle of friction. Suppose in field, in many cases, you can't get only cohesive soil, that is pure clay or pure sand. Okay, you will get mixture. Suppose silty sand. Okay, you will get a mixture of both the soil. Actually, so suppose is silty sand. If you conduct tests, you will get both C and phi values. Okay.
Okay, sir.
Okay. For pure sand, there is no C, and for pure clay, there is no phi. But for silty sand and the mixture of clays and sand, you will get both. Okay.
Okay. So, for clay soil, we don't have C or phi.
For clay soil, you have only C value, only cohesion
C
value.
value.
For pure clay, okay, for pure clay.
Okay.
Okay. Mm, okay. So we have both the C and phi values over here. We know the unit weight of this part, that is the part above the groundwater table, that is the gamma 17.5 kilometer per meter cube, and gamma saturated we also know that is the saturated unit weight of soil, that is 18.5 kilometer per meter cube. So you see this part is fully underwater, that is underground water. So this part is saturated. So we need the saturated unit of soil, that is the gamma submerged. Sorry, this is fully submerged. So from saturated, we will calculate the submerged unit weight of soil. So what is submerged unit of soil? We just have to deduct the unit weight of water from the saturated unit weight of soil. Okay. So the effective surcharge at depth df. Okay, this one is at depth df. So what will be the surcharge at depth df? You see this height, this is the height of the groundwater table, depth of groundwater table below the ground surface. So this one is dw. See dw, what is the unit weight of this part? It is gamma, plus this portion, the from the starting of from the top of water table to the base of foundation. The what is the height of this one is df, that is the total depth of foundation, the depth of the foundation minus the depth of the water table from the top. So you see this one is the height, and I have multiplied this with the submerged unit weight of soil. Okay, so now over here, see, I have did this. So now, so I have done this, and after that, for phi equal to 35 degrees, for phi equal to 35 degrees, if you refer to the Terzaghi's bearing capacity factors chart or the formulas, that is NC, N gamma, NQ, all those things, from the chart you will get the values NC equal to 57.5, 57.8, NQ is equal to 41.4, and N gamma is equal to 42.4. NC is 57.8, NQ equal to 41.4, and N gamma equal to 42.4. So now we need to find out QNS. Okay, QNS for the first part, that is when the groundwater table was 1.25 meter below the ground level. So what is QNS? QNS is actually Q of net ultimate bearing capacity divided by factor of safety. We also have factor of safety, which is 3. You see, 3. Factor of safety is 3. So first of all, we need to find out the QNU. QNU. So what is QNU? What is the formula? formula is CNC plus Q NQ minus 1 plus half into gamma B in gamma. You see, this is a strip footing, okay? You see, this is a strip footing. So that means the shape factor is only half this, there will be no shape factor. So the shape factor is 1. So now, what is the value of C? So what is the value of C? Value of C is 30 kPa. So 30. What is the value of NC? NC is 57.8. And what is the value of Q, which we found out? It is 28.39. And value of NQ is 41.4. It is minus 1 minus half into C. For this part, you see this is totally submerged. So for this part, this will be gamma submerged. So half into what was the submerged value? 8.69 into breadth. What is the breadth of the foundation? It is 3 meter. 3 meter, and N gamma is 42.4. And this will, and if you calculate this, you will get 3433. I will recommend you to calculate this, okay, because I may be wrong also. 64 kilonewton per meter square. This is the value of net ultimate bearing capacity. Now we need to find out the net safe QNS. So what is QNS? QNS is equal to QNU divided by factor of safety, and the factor of safety in this case is 3. So it is 3433.64 divided by 3, and this comes to be 1144.55 kilonewton per meter square. This one is the answer of the first question, that is 1A. Do you have any doubts? If you have any doubt in this question, you may ask. If you have any doubts, you may ask now, okay? Or else I will proceed to the next part.
So please turn the second slide
Okay, this one,
where you solve.
this
Uh,
one. Okay.
yes, sir. So where from where we find the N, C, N, R, and Q values?
Yes, I'm telling you.
Yeah.
There are charts, you know. Let me show you. What was our phi value? What was our phi value for the last question? For this question? I think it is 35 degree, right?
Yes, sir. 35 degree.
You see for 35 degree, please refer to the 35 degree and you can see the corresponding bearing capacity factors. You can refer to any book, you will get these values. This book, Ranjan and Gopal Ranjan and Rao, 1991, and all the other
So, sir,
books.
we have to remember these values, or in exams we can get these values.
In exam, you will get these values, and also,
Okay.
and if this chart is not given, the formulas will be given. You see in the left hand side there are the formulas for NC, NQ, and gamma. If you calculate using these values, you will get use. If you calculate using this formula, you will get these values only. If you put phi over here,
Okay.
okay.
Sir, but what are you showing this chart? We can't see.
1 minute. Can you see this table?
No, sir. We are not able to see that.
Uh, oh, 1 minute, 1 minute. Sorry. Can you see the table now?
Yes, sir.
So this is the table, okay? These are the formulas. In the left hand side, you can see there are formulas for NC, NQ, and gamma.
Yes,
And
sir.
if you put phi, you know the value of phi. If you put all these things, phi, and do you know what is Kp over here? In gamma, you can see there is Kp. Do you know what is Kp?
No, sir.
Kp is the passive resistance coefficient. Okay, it is calculated like 1 plus sine phi divided by 1 minus sine phi. Okay, you will know. I will do some of those problems later. So
Okay.
you see if you put or if you use these formulas, you will get these values only. So for 35 degree corresponding bearing capacity factors, you can see in the chart. You see
Okay.
NC is equal to 57.8, NQ equal to 41.4,
41.4.
and N gamma is equal to 42.4. You see?
42.4. Yes,
So
sir.
okay.
Thank you, sir.
Okay. So this is the answer for the first part. So I believe you all have understood. So now I'm proceeding to the second part. So what was the second part? In the second part, it is showing over here that the groundwater table is 1.25 below the base level of the foundation. 1.25 meter below the base level of the foundation. Okay. So that means this one is your foundation. This one is DF equal to 2 meter, equal to 2 meter, and the breadth is 3 meter. And your groundwater table in the second part is 1.25 meter below the base level of the foundation. So it is 1.25 meter below the base level of the foundation. Okay. So here is the groundwater table, GWT. So you see from the base of the foundation up to depth B, B means the breadth of the footing, up to depth B, that is 3 meter, there will be effect of there will be, if you cross beyond the depth B from the base of the foundation, suppose this line, okay, if the groundwater table is below, suppose this groundwater table is over here or beyond, suppose over here, okay, Suppose the ground water table is over here or over here, that is beyond, that is at depth b from the base of the foundation or beyond that. Greater, suppose this is the groundwater table depth. It is the in this problem the groundwater table depth is over here, that is 1.25 below the from the base of the foundation. And if the groundwater table depth is greater than b from the depth of the foundation, suppose it is over here or maybe over here, in those cases we do not need to consider the effect of groundwater while calculating the bearing capacity of the footing. Okay, there will be no effect. That means the groundwater table is at a great depth and it will cause no effect on the bearing capacity. So in those cases, we do not need to consider the effect of groundwater table. But in this particular case, we can see the depth of the groundwater table is at 1.25. When what is the breadth of the foundation? It is 3 meter. Okay, so see the breadth is suppose 3 meter and the groundwater table is over here at 1.25 meters. So we need to consider the effects of groundwater table in while calculating the bearing capacity or anything, net bearing capacity, net ultimate bearing capacity, and everything we need to consider the effect of groundwater table. So for that, what we need, so for finding the net of ultimate bearing capacity, we need to find out the net ultimate bearing capacity first. So what is the formula? CNC plus Q into NQ minus 1 plus half B in gamma. Now here it will be gamma dash. Okay, so we will incorporate the effect of groundwater table using this gamma dash. So what is gamma dash? Gamma dash is equal to, there is a formula, gamma submerged plus B by B gamma submerged. So now what is small b? The small b is the depth of the groundwater table from the base of the foundation. So b is equal to 1.25 meter. Okay, b is equal to 1.25 meter. So we know b, we know this also, this one is the breadth of the foundation. We know what is gamma and we also know the gamma submerged. Okay, so gamma dash, I am writing it 1 second over here. So what is gamma submerged? Gamma submerged is this one, 8.69 kiloliter per meter. 8.69 kiloliter per meter cube. And what is the value of B? Small b is 1.25. Groundwater table is at a depth of 1.25 below the base of the foundation, that is 1.25. So B, small b is equal to 1.25. Capital B, what is capital B? It is the breadth of the foundation, that is 3. And what is gamma? That is the saturate, that is the unit weight of this part above the groundwater table. What is the unit weight of soil above the groundwater table? I guess it is over here. I have written 17.5. 17.5 minus saturated submerged unit weight is 8.69. So if we calculate this, you will get 12.36 kilonewton per meter cube. Now, what is the formula for QNU? QNU is CNC plus Q into NQ into NQ minus 1 plus half into B in gamma gamma dash. So now if we put all the values in this equation, the value of C, I guess it is 30 kPa. NC is oh, NC is how much is NC?
57.8.
57.8. And the Q that we calculated, what is the value of Q? I think
28.39.
okay, 28.39. And what is the value of NQ?
41.4.
Yes, plus half into what is the breadth? 3 meter. And what is the value of N gamma?
N gamma is 42.4.
42.4. And this one is gamma dash. So this one is 12.36.
12.36.
So if you calculate this equation, it will be 3517.05 kilonewton per meter square. Okay. So now we get the value of, from here we have determined the value of QNU. Now we need to determine the value of QNS. So QNS will be equal to QNU divided by factor of safety. So so you know the value of QNU now. Just divide it using factor of safety. You will get the value of QNS. Okay. So now let's come to the second problem. One. Please wait for a minute. Okay, so now let us come to the second question. So the second question is, a rectangular footing of size 2 meter by 3 meter, 2 meter by 3 meter is founded at a depth of 2 meter in a homogeneous Cephei soil. The water table is 1 meter below the ground level. So we have the B value over here. B is the breadth of the foundation is 2 meter. The length is 3 meter. Is founded at a depth of 2 meter in a homogeneous Cephei soil. The depth of the foundation is 2 meter. The water table is 1 meter below the ground level. So let me draw it once. This one is your foundation. This is the depth of the foundation, 2 meter. And the water table is 1 meter below the ground level. Water table is 1 meter below the ground level. The unit weight of soil above the water table means this one is over here. This is water table. The unit weight of soil above the groundwater table means unit weight of this part. This part is gamma is 18 kilonewton per meter cube. The saturated unit of soil is 20 kilonewton per meter cube. Determine the rigidity index and the critical rigidity index of the soil. That is, we need to determine IR and ICR of soil. Consider C is equal to 50 kPa and phi is equal to 30 degrees. The modulus of elasticity of soil is 5 MPa. E value is 5 MPa. And the Poisson ratio of soil is 0.35. The load is vertical and acts at the center of foundation. Comment on the correction factors due to soil compressibility. Okay, first let us focus on this part, on the first part. We need to find out the rigidity index and critical rigidity index. So, what is the formula for the rigidity index? That is IR. There is a
Sir, sorry
hmm,
to interrupt, but can you please um, tell us about the rigidity index and critical rigidity index?
yes, yes. In basics bearing capacity theory, we know about soil compressibility, compressibility, right? In Tarzagi, the when Tarzagi derived the bearing capacity theory, he considered that the soil is incompressible, but it is not right, right?
Yes.
So soil is compressible. So in order to incorporate the effect, what in case of suppose if you see in local shear failure, what Tarzagi did to incorporate the compressibility effect, he introduced some factors like he reduced C by 2 by 3 and also phi. So 2 by 3 10 phi like that. He reduced phi value and C value, right? To incorporate the compressibility effect. Okay. So
Okay.
what basic did is that basic thought basic what basic told is that basic told that by reducing phi and c like that, by reducing phi like by 2 by 3 factor and phi by 2 by 3 also, that is very conservative because it is decreasing very much, so that is not actually right. So what basic did is that basic introduced this rigidity factor, indexes. So rigidity, we need to find out the rigidity index IR, and after that we need to find out the critical rigidity index. So when the rigidity index of soil is greater than the uh, when the rigidity index of soil, that is when IR is greater than the IRCR, that is the critical rigidity index of soil, that means the soil is very stiff, it is not compressible. So to incorporate the this rigidity, the compressibility factors, there are some factors. The factors are CC, CQ, and C gamma. All these factors are incorporated into the bearing capacity formula, like the Sheff factors and Def factor. Okay, to incorporate the compressibility effect. Now, if IR rigidity index is greater than the critical rigidity index, at that point of time, all these factors becomes one, because the soil is very stiff, it is more or less not compressible. But when rigidity index is lesser than the IRCR, we need to find out these factors. This CC, CQ, and C gamma, all this will be lesser than 1. Okay, all these values will be lesser than 1 at that time when IR, that is a rigidity index, is lesser than critical rigidity index. That means the soil at that point time, when in this case, when rigidity index is lesser than the critical rigidity index, in this case, the soil is not that compressible. Soil is not incompressible actually. It is compressible a bit.
Okay. Thank you,
So,
sir.
so I hope you have understood what I'm trying to say.
Yes,
Okay.
sir.
Okay.
Yes, sir.
So IR. So what is IR? IR is equal to G. That is the shear modulus of the soil divided by C plus Q dash. That is the effective surcharge. Effective surcharge at depth df plus b by 2. Okay. Df means the depth of the foundation plus breadth of the foundation by 2. We need to find the surcharge, effective surcharge at this depth, and Q dash into tan phi. So now, so we know the Young's modulus of soil, that is the modulus of elasticity, that is 5 MPa. So E is equal to 5 MPa. But we do not know the value of the shear modulus. So we need to find out the shear modulus from E. So do you know this formula? E by, I believe you have all studied this formula in solid mechanics. We will use this only. So what is the value of E? E is 5 ampere. That means 5 into 10 to the power 3 kilonewton divided by 2, 1 plus what is the Poisson's ratio? It is 0.35. This one is the Poisson's ratio. So if you calculate this, the G value will be 1852 kilonewton per meter square. Now, what is the value of Q dash at df plus b by 2? What is the value of Q dash at df plus b by 2? So df is 2 meter and b is the breadth of the foundation is how much?
3 meter.
uh,
2 by 2 meters. Sorry.
breadth of the breadth 2 meter. So what is df plus b by 2? It is 3 meter, right?
3 meters.
Hmm.
Yes, sir.
Okay. So we need to find out Q dash at 3 meter. So it is, see, this one is gamma, gamma into 1, gamma into this depth, this part, this depth, 1, 1 plus plus this one is 1 meter, that is the dA plus V by 2. So B is, if B is 2 meter, then this one is 1 meter. So this part, this, so how much is this part? This part is 2 meter, right? 2 meter, 2 plus 1. So 2 into submerged unit weight of this part. So what is the submerged unit weight? Hello friends, can you switch off your microphones? If you have any doubt at that point of time, you please switch on, okay? So, so what is the value of gamma?
0.35.
No, this gamma, this one.
18 kilonewton.
Yes, the unit weight of this part, that is the soil above the groundwater table. Okay, so 18. 18 into 1 plus 2 into submerged. What is the unit weight of saturated unit weight of soil? So this one is gamma sat minus gamma W. So what is the saturated unit of weight of soil?
20 kilonewton per meter cube.
20. And what is the unit weight of soil? Unit weight of water?
9.81.
Okay, I'm considering 10. Okay, 10.
Okay.
So how much? So if you calculate this, it will be 38 kilonewton per meter square. Okay. Now IR. IR is G by C plus Q dash tan phi. G by C plus Q dash tan phi. You know the value of G, right? What is the value of G? This one, 1852. 1852. You also know the value of C, 50 kPa. 50 kPa. Plus you also know the value of Q dash at df plus b by 2. It is 38. And what is the value of phi? 30 degrees. If you calculate this, you will get 25.74. See, there is no unit because it is an index. There will be no unit. The unit weight of C and Q dash is kilonewton per meter square, and the unit weight of G is also kilonewton per meter square. So both are kilonewton per meter square, so there will be no units. This is an index. So IR is rigidity index is 25.74. Now let's look at the second part. So critical rigidity index of soil, that is we need to determine IRCR. So what is IRCR? There is a formula for that. That is half exponent E into 3.3 minus 0.45 B by L cot of 45 degree minus 5 by 2. Okay. Now if we put all the values in this equation, if we put all the values in this equation, that is 3.3 minus 0.45, what is the value of B? It is 2 and length is 3. Cot of 45 degree minus what is the value of phi? I think it is 30 degree. So 30 by 2. If you solve this, if you solve this equation, we will get IRCR value 90.3. So IRCR is 90.3 and IR value is 25.74. So that means IR value is much lesser than IRCR. Okay. See, IRCR. So here there is a statement, comment on the correction factors due to soil compressibility. So as I have told earlier, if the rigidity index of soil is lesser than the critical rigidity index of the soil, in this case the soil will be compressible. So if the soil is compressible, the correction factors, that is Cc, C gamma, Cq, all these factors will be lesser than 1. So this is the comment. Okay, all the correction factors which we incorporated into the bearing capacity equation, all those factors will be lesser than 1.
So, what is EXP?
Exp means e, exponent.
Uh, we
Means
didn't put this its value.
uh, e means exponent, that is e to the power this. Okay.
Okay.
Okay. Calculate this part and just e to the power of that value. Okay. E to the
Okay,
power
sir.
of that. Okay. Now let's come to the third question. What is the third question? A square footing fails by general shear in cohesionless soil deposit. So there will be no C. It is a complete cohesionless soil on having phi equal to 40 degrees under an ultimate load. Ultimate load. What is the ultimate load? 5500 kilonewton, 5500 kilonewton. The footing is placed at a depth of 2 meter below ground level. The unit weight of soil given is 18 kilonewton per meter cube. So since this is a complete cohesionless soil, there is no C. That means C equal to 0. So that means this part, CNC part, will be 0 totally. So that is why there is no CNC. That is there is no NC. Only NQ and N gamma are given. Determine the size of the footing if the water table is founded at a great depth. Use Tarzagi's theory. Okay. Determine the size of the footing. We don't know its size. Only we know that it is a square footing. Okay. So suppose if the width of the square footing, suppose the width is B. Suppose the width is B. So what will be the area of the square footing? B square, right? So this one is the ultimate load. Q ultimate is equal to 5500 kilonewton. That means the foundation can take this much load. This is the ultimate. Beyond this load, it will fail. So we can also find out the ultimate bearing capacity value from this. How? Q ultimate divided by area, that is 5500 by B square. This one is the ultimate bearing capacity of soil, because if you cross this value, if you cross this stress, if you stress the foundation beyond this value, there will be failure, shear failure in the soil. So this one is the QE. Okay. And we also know the value of the formula for QU. What is the formula for QU? CNC plus QNQ plus half. So this is a square footing. So there will be a shape factor, right? Zero point 0.4 is the shape factor. And here will be 1.3. But this part is 0 since this is a cohesionless soil. Gamma B and gamma. Okay. So what is the value of 540 degrees? For phi, for phi equal to 40 degrees, NQ and N gamma is already given. For phi equal to 40 degrees, NQ and N gamma is already given. NQ is 81.3. N gamma is 100.4. Now the footing is placed at a depth of 2 meter below the ground level. So suppose this is a footing, this one is 2 meter below the ground level, and water table is founded at a great depth. So there will be no influence of water table. So there will be no influence of the water table. So what is the effective surcharge value at depth df? So this one is the surcharge. So q equal to q n q plus 0.4 gamma b n gamma. So q is what is the unit weight of soil? Unit weight of soil is 18 kilonewton per meter cube. That is gamma. So gamma is 18 kilonewton per meter cube. So this Q will be gamma into depth. What is the depth? 2 meters. So Q is gamma into D, that is 18 into 2. So it will be 18 into 2. And what is the value of NQ? NQ is 81.3. So here it is 0.4. And since there is no effect of water table, there will be gamma only. So gamma is 18 over here. And what is the breadth? Breadth of the foundation is square footing, we don't know. So breadth is B. And what is the value of n gamma? 100.4. And we also know this QU. QU, this one, 5500 by B square. So if we equate both these things, because both these things are same. So if we equate these two things, 5500 by A square, that is area, sorry, A square means B square. B square is equal to, if you solve this part, you will get uh, 2926.8 plus 722.9 into B. So 5500 is equal to 2926.8 B square plus 722.9 B cube. B cube. I am just multiplying this part with B square. So you will get this equation. Now if you solve this equation, you will get, if you solve this equation using calculator, you will get the value of B as 1.2 meter. Okay, it is a square footing, so the dimension is 1 by 2 by 1 by 2. Wait for a minute, please. So the fourth question. What is the fourth question? Fourth question is a strip footing of 3 meter. A strip footing of width 3 meter, that is the B, is founded at a depth of 1 meter in a homogeneous sandy soil deposit. The water table is at a great depth. The unit weight of soil is 18 kilonewton per meter cube. Determine the net safe load if phi equal to 40 degrees and C equal to 0. This is a complete cohesionless soil. The load is vertical and acts at a distance of 0.2 meter from the center along the center line of the foundation in width direction. That is, in this case, the foundation has an eccentricity. Okay. That means the load is not acting at the center of the foundation. Use Mayer equation and assume general shear failure and factor of safety of 3. We can here the NQ and N gamma values. No NC is given. So because this is a complete sandy soil, C is equal to 0. So CNC part will be also 0. That is why NC is not given. So now let us solve this. B is equal to 2, B is equal to 3 meter. B is equal to 3 meter. So B is equal to 3 meter and EB, that is the eccentricity value, is 0.2 meter. It is along the breadth. Suppose this one is length, this one is breadth, this one is the center line, and suppose the load is acting over here, okay, along the breadth EB. So EB value is 0.2 meter and the depth of the foundation is 1 meter. And the depth of the foundation is 1 meter and the water table is at a great depth, so there will be no influence of water table. The unit of soil, that is gamma, is 18 kilonewton per meter cube. Determine the net safe load if phi equal to 40 degrees, 40, and C is equal to 0. The load is vertical and acts at a distance of 0.2 meter from the center line of the foundation. So EB is 0.2 meter. Use Mayer equation and assume general shear failure and a factor of safety of 3. F is 3 and NQ is 64.1, N gamma is 93.7. We need to find out the net safe load. Okay, so for net safe load, we need to find out the net ultimate load, net ultimate bearing capacity. So net ultimate bearing capacity. The formula is CNC into SC, DC, IC. All these are factor, shape factor, depth factor, and influence factor, inclination factor, plus gamma DF, NQ, SQ, DQ, IQ, plus half into B dash gamma. Why B dash? Because there is eccentricity. We need to find out the effective breadth. Okay, we need to find out what is the effective breadth. I will show you. N gamma, S gamma, D gamma, I gamma. Okay, minus of surcharge. What is the surcharge? Because this is the net ultimate. So we need to subtract the surcharge. That is the gamma df. So now for strip footing, this is a strip footing. So for strip footing, the shape factors SC, SQ, and S gamma, all these are 1. And since there is no inclination, that is, it is totally on the ground and there is no inclination, there is no angle. So IC, IQ, and I gamma is also 1. because there is no angle and no inclination, nothing, and the base is also horizontal. We need to calculate the depth factors. For the depth factors, we need to find out b dash. So what is b dash? B dash is b minus 2eb, because the eccentricity is along the breadth. So what is the b value? B value, the breadth of the foundation is 3 meter. So 3 minus eccentricity. What is the eccentricity? It is 0.2 meter. So 3 minus 2 into 0.2. So this one is 2.6 meter. So now this one is total. This is a complete questionless soil. So C is 0. That means this part is 0. So only this part. So this SQ is SQ, DQ. All these are SQ and IQ and S gamma, I gamma. This SQ, IQ, S gamma, I gamma. All these are 1. So we need to find out DQ and D gamma. Okay. So DQ. And the formula for DQ and D gamma are same according to Mayorov equation. So DQ equal to D gamma, the equation is 1 plus 0.1 root over of Kp df by b dash. Now Kp, what is Kp? Kp is the earth pressure coefficient for passive resistance. Kp is the earth pressure coefficient for passive resistance. This one is 10 square 45 degree plus 5 by 2. This is the value of Kp. This is the value of Kp. So what is the value of phi? What is the value of phi? It is 40 degrees. Okay. 10 square 45 degree plus 40 by 2. This one. So this one is Kp. Okay. So what is, so now we know the value of df, that is the depth of the foundation. It is 1 meter. Df, this one is 1 meter. You can calculate Kp using this formula. You know also the value of b dash. Okay, so now if you put all these things, you will get dq equal to d gamma. This one, it will be 1.0825. Okay, this one will be 1.0825. So now, what was the question? We need to find out the net safe load. The net safe load. Okay, so for net safe load, we need to find out the net ultimate bearing capacity, that is the QNU. The QNU, so the QNU, it will be gamma df nq dq, gamma df nq dq plus half into b dash, half into b dash gamma n gamma, gamma gamma n gamma and d gamma. Now let's put all the values over here. What is the value of, what is the unit weight of soil? It is 18. And what is the depth? The depth is 1 meter. And what is the value of NQ? 64.1. And what is the depth 1 64.1. And what is the value of dq? Because all the factors, all the other factors, that is sq and iq, all these are 1, so I'm not writing sq, iq, s gamma, I gamma, all these are 1. So what is the value of dq? Dq is 1.0825. 1.0825 plus half. What is the value of b dash? This one is the value of b dash, 2.6. 2.6 into unit weight of soil 18, and n gamma. What is the value of n gamma? N gamma is 93.7. And there is also d gamma. D gamma is same as that of dq, which is 1.085. And there is another part. After that, there is gamma df. We need to subtract the surcharge because this is the net unit, net ultimate, not ultimate. So minus gamma into df. So we need to subtract 18 into the depth of the foundation, unit weight into depth. Unit weight is 18 and depth of the foundation is 1 meter. So this one. Now, if you calculate this, you will get 3604.5 kilonewton per meter square. This is the net ultimate bearing capacity. That is the net ultimate bearing capacity. This one is in the form of stress. And the question is, you need to find the net safe load. Okay. So we know now the net ultimate. We need to find out from net ultimate, we need to find out the net safe bearing capacity. From net safe bearing capacity, we need to find out the net safe load. So from net safe, from net unit, we need to find net ultimate, we need to find out the net safe. So ns equal to q nu by f. So 3604.5 by factor of safety. What is the factor of safety? It is 3 divided by 3. Okay. So this one is 1201.5 kilonewton per meter square. Okay. So what is the net safe load? We just need to multiply this with the area. It is net, this one is net safe load. Net safe load. So what is the, this one is 1201.5 qns into area. 1201.5, and this is a strip footing. So what is the area? Area is 3, the breadth is 3 meter. Since the length is very large, we will find out the net safe load per unit area. Okay, I am considering the length to be 1 for per unit area, per unit length, since the length of the strip footing is very long. So okay, so area is 3 into L, that means 3 into L divided by L. Okay, this L is cancelling each other out. So 1.1201.315 into 3. This one will come, this one comes to be 3124 kilonewton per unit length of the strip footing. If you have any doubt in this problem, you may ask.
So please explain again this question.
Okay. So in this question, you see the strip footing of width 3 meter. The width of the strip footing. See, the length of the strip footing is very long. Okay, it is a very long compared to its breadth. The length of the strip footing, in case of strip footing, its length is very long compared to its breadth. So the breadth is here, width is 3 meter, is founded at a depth of 1 meter. DF is 1 meter in a homogeneous sandy soil deposit. It is a completely cohesionless soil. That means there will be no C, only phi. The water table is at a great depth, so there will be no influence of water table. The unit weight of soil is 18 kilonewton per meter cube. And the question is determine the net safe load if phi equal to 40 degree and C equal to 0. C is equal to 0, obvious, it's obvious. The load is vertical and acts at a distance of 0.2 meter from the center along the center line of the foundation in the width direction. So that means the load is acting at a distance of 0.2 meter from the center line along the width direction. This one is width. See, this one is length. It is very long. This one is very long. Along the width direction, the load is acting. Along the width direction, the load is acting at a distance of 0.2 meter. Use Mayer equation. Assume zero range shell failure and factor of safety of 3. Use the bearing capacity factors Nk equal to 64.1 and N gamma equal to 93.7. So B is equal to 3 meter, df equal to 1 meter, eb equal to zero point 0.2 meter, and c equal to 0. Factor of safety 3, nq and n gamma are given. Okay, so this qnu is the bearing capacity equation for net ultimate bearing capacity. So c is 0 because it is a sandy soil, complete cohesionless soil. So c is 0, that means this part is total 0. So the rest part is gamma df nq sq dq iq plus half into b dash gamma into n gamma s gamma d gamma I gamma. Now since this is a strip footing, all the shape factors, and since this the base of the footing is horizontal and no yeah, the load is acting vertically, so the inclination factor is also 1. The load inclination factor is also 1, and the shape factor is also 1. See, IC and SC, SQ, all these are ones, and this is a strip footing, and that is why the shape factor is also 1. And since the load is acting vertical, here it is also mentioned that the load is acting vertical. So that is why the inclination factor is also 1. It's inclination factors. So we need to find out the effective breadth since there is eccentricity. So effective breadth equal to B minus 2 into EB. EB means eccentricity along the width direction. We need to, so B is the width is 3 meter minus 2 into 0 0.2. We are getting here 2.6. But we need to determine the depth factors, that is dq and d gamma, to for solving the equation for qnu. So dq and d gamma is the formula is same for dq and d gamma. It is 1 plus 0.1 root over of kp into df by b. So what is kp? Kp, as I have told earlier, it is the coefficient of passive resistance. So Kp is equal to tan square 45 plus phi by 2. We know the value of phi. It is 40 degree. It is mentioned over here. So it is 40 degrees. So tan square 45 plus phi by 2. So you know, so you can solve dq and d gamma 1 plus 0.1 root over of Kp df by b dash. You know what is b dash. This one is b dash, and you know the value of df, that is 1 meter, the depth of the foundation. If you put all these things in this equation, you will get the value of depth factor, which comes out to be 1.0825. Now put it in the equation, put it in this equation, put all the values in this equation. You know gamma, you know df, you know nq, you know dq. This is dq and d gamma. You know everything. Half into b dash gamma n gamma d gamma, gamma into df. You all know, you know all these things. So you know all the values of all the parameters. So if you put all this all the values of all the parameters in this equation and solve, you will get this and this value. This is the net ultimate. And if you divide the net ultimate bearing capacity by factor of safety, you will get net safe bearing capacity. This one is the net safe bearing capacity. And here it is asking, and here in this question, The question is asking for net safe load. How much load we should apply? How much safe load we should apply? So we know the value of net safe bearing capacity, that is 1.01.5 kilonewton per meter square. And if we multiply this value with its area, the area of the foundation, we will get the net safe load. And since this is a strip footing, the length is very long and the length is also unknown because this is strip footing. We need to find the area. Suppose the length is L and we need to find out the load in terms of per meter length. Okay, per meter length. Suppose the length is L, so 1.25, 1.5 into 3. 3 means 3 is the breadth. uh, Strip footing is like this. This is the breadth and this is the length, rectangular. So this one is breadth. So how much is the area? B into L. B is 3 meter, length is unknown. So 3 into L, and per meter length means I am dividing this whole thing by L. So L is cancelling out. So 1.01.5 into 3. That comes out to be 13124 kilonewton per meter. So have you understood?
Yes, sir.
Okay.
Thank you, sir.
Okay. Okay. So the fifth question. So what is the fifth question? A rectangular footing of size 2 meter by 3 meter. A rectangular footing of size 2 meter by 3 meter is founded at a depth of 1 meter in a homogeneous C5 soil deposit. The water table is at a great depth. The unit weight of soil is 18 kilonewton per meter cube. An eccentric vertical load is applied. Two eccentricity here in this case. EL is equal to 0.5 meter and EB equal to 0.4 meter. Determine the effective area of the footing. C equal to 100 kPa, phi equal to 20 degrees. Use Heiter Anders 1985 approach. So what are given over here? We need to first write down the parameters that are given over here. So B is 2 meter, L is 3 meter, depth of the foundation is 1 meter. It is a C5 soil. That means there will be both C and phi. The water table is at a great depth, so that means there will be no influence of water table. The unit weight of soil is 18 kilonewton per meter cube. An eccentric vertical load is applied to eccentricity. The eccentricity along length is 0.5 meter and eccentricity along breadth is 0.4 meter. We need to determine the effective area of the footing. C is equal to 100 kPa, phi is equal to 20 degrees. We need to use Heiter Anders method. So first of all, let me draw this thing. Suppose this is the plan, the top view of the footing. This one is the center line. The load is acting over here. This one is the eccentricity along B, EB. And this one is the eccentricity along length, EL. We know the value of EL and EB. Okay. So the effective area will be like this. In this case, the effective area will be like this. This one is the value of B1 from this end to up to this end. It is B1 and up to this part. It is L1. So what is EB by B? We need to first find out EB by B. What is EB by B? EB is 0.4 and breadth of the footing is 2 meter. So EB by B is 0.2 and 0 EB by B 0.2, it is greater than 1 by 6. We need to also find out EL by L. What is EL by L? 0.5 by 3. It comes out to be 0.167. So this one is equal to 1 by 6. Okay. So now in this case, so as in the course you must have seen, for this case when EB by B is greater than equal to 1 by 6 and EL by L is also greater than or equal to 1 by 6. In this case, B1, that is this value B1 and L1 is equal to B, that is the original breadth, 1.5 minus 3 into EB by B. Okay, and L1 is equal to L into 1.5 minus 3 into EL by L. Now if we put all the values of all the parameters in these two equations, you know the value of B, you know the value of EB, you know the value of B also. You know this L, you know the value of this L. If this one, see, EB, EL, L and B. Okay, let's put uh, B is 2 meter, 1.5 minus 3 into EB by B. What is EB by B? EB 0.4. What is B? 2. And this one, what is L? L is 3 meter. 1.5 minus 3 into EL. What is EL? EL is 0.5. And this L is 3 meter. Now if we solve these two, B1 will be equal to 1.8 meter and this L1 will be equal to 3 meter. Now L dash, okay, L dash is equal to maximum of B1 and L1. So what is the maximum of B1 and L1? It is 3 meter. So L dash is equal to L1 is equal to 3 meter. So A dash. So L dash is equal to 3 meter. L dash is equal to 3 meters. Now if we look at this area, you see this is a triangle. This is a complete triangle, this shaded area, and the length of this side is L1 and this side is B1. Okay. So what is the value of B1? B1 is 1.8. And what is the value of L1? L1 is 3. So A dash will be equal to half into L1 B1, because there is no need to incorporate this because L dash and L1 both are same, so I am writing L1 over here. So half into, what is L1? L1 is 3 meter, and what is the value of B1? B1 is 1.8 meter. It is 2.7 meters. This is the effective area of the footing, means load is so load will affect only this area, only this shaded area. This is the effective area. If you have any doubt, you may ask. Okay, so next question, question number 6. Question number 6 is a rectangular footing of size 2 meter by 3 meter is founded on a homogeneous C5 soil deposit. This one is B, this one is L. 3000 kilonewton load acts at an angle of 10 degrees to the vertical. Load is acting at an angle of 10 degrees to the vertical at the center of foundation. C is equal to 75 kPa, phi is equal to 25 degrees. The net ultimate bearing capacity of the foundation is 1250 kPa. Determine the factor of safety against bearing and sliding. Take this one is the angle of friction between the footing and the soil. It is 0.8 of phi. And this one is the adhesion, Ca base. Adhesion factor between the base of the foundation and the soil. It is 0.7 C. Neglect the passive resistance. So what is happening in this case? So what is happening in this case? Suppose this is the footing, okay? This is the footing. The breadth of the footing is 2 meter. It is a homogeneous C5 soil deposit. 3000 kilonewton load acts at an angle of 10 degrees to the vertical at the center of foundation. So if this is the center of foundation, load is acting like this, okay? P is 3000 kilonewton at an angle of 10 degrees to the vertical. This angle is 10 degrees. So alpha is equal to 10 degrees. C is equal to 75 kPa. Phi is equal to 25 degrees. The net ultimate bearing capacity, QNU is 1250 kPa. Determine the factor of safety against bearing and sliding. Okay, the friction between the base of the foundation and the soil is taken as 0.8 phi. What is phi? Phi is 25 degrees. And the adhesion between the base and the soil is 0.7 C. Neglect the passive resistance. So what is happening over here is that the load is acting at an angle. So that means since the load is acting at an angle, this is an angle, this is the vertical and horizontal, there will be both components, vertical and horizontal components, like this. This is the vertical component, this is the horizontal component. What will be the vertical component? If this is P, vertical component will be P cos alpha, and the horizontal component will be P sin alpha. And due to this, so V will be P cos alpha, and the horizontal component will be P sin alpha. Okay, the horizontal component, vertical component, and this horizontal component will try to push this foundation in this direction, right? The horizontal component will try to push this foundation in this direction. That means it will slide, it will try to push the foundation, and and this will cause sliding, okay? But the soil beneath the ground will also provide resistance in this direction, okay? Will also provide shearing resistance in this direction. Okay, so we need to find out the bearing capacity against sliding in this case. And when we need to find out bearing in case of when the axial load is acting. Okay, when by considering only the axial load, we'll find out the bearing, and by considering this horizontal load, we'll find out the sliding, the factor of safety against sliding, because the horizontal load is causing the sliding of this foundation, and the vertical load, we will consider that to find out the factor of safety against bearing. So now, factor of safety against bearing. What is the factor of safety against bearing? It is, we know the bearing capacity of the foundation, that is Q into uh, net ultimate bearing capacity of the foundation, that is 1250 kPa. QNU is equal to 1250 kPa. We know this. So factor of safety against bearing, we will consider only the vertical part of the load in this case. So factor of safety against bearing. So we know this net ultimate bearing capacity. So what is the maximum load that foundation can carry? We know the net ultimate bearing capacity, and if we multiply this 1250 with the area of the foundation, we will get the maximum load that the foundation can carry. So QNU into area, this is the maximum load that the foundation can carry. If we divide this with the vertical load that is currently acting, the vertical component that is currently acting on the footing, we will get the factor of safety. So what is the vertical load that is acting on the footing? It is P cos alpha. You see, the vertical component is P cos alpha. P cos alpha. So Q into Nu is 1250 kilonewton. Area, what is area? Breadth is 2, L is 3. The breadth is 2 meter, L is 3 meter. So 6 meter square. P cos alpha, what is P? P is 3000. Cos alpha, what is alpha? Alpha is 10 degrees. See, 10 degrees. Alpha is 10 degrees. That is the inclination of the load, of the resultant load to the vertical axis. So this one, it is 10 degrees. 3000 kilonewton acts at an angle of 10 degrees to the vertical. So 10 degrees. Now, if we solve this, we will get 2.54. So factor of safety against bearing is 2.54. So that means it is safe against bearing. So that means the so that means 3000 kilonewton will not cause any failure by if we consider the bearing. That means it will not cause any shear failure in the soil. But in case of sliding, will it slide? We need to check that whether the factor of safety against sliding is greater than 1 or less than 1. We need to check that. Factor of safety against sliding. So for a factor of safety against sliding, we need to find out the what I have told earlier. The horizontal component of P of load P is pushing this foundation in this direction, is trying to push the foundation in this direction. So soil is also providing a resistance in this direction. Okay, this happens, or else the foundation will move. If there is no resistance, the foundation will move in this direction. But it doesn't happen because soil is providing resistance, and it is much greater than the sliding force. Okay, the force that is trying to make this foundation slide. and the horizontal resistance is much greater. So what is the horizontal resistance? Horizontal resistance of horizontal resistance of the soil is defined as the H value. The horizontal resistance we denote it by T. Why the so T, the formula for T is area into CA. CA means the adhesion between the base and the soil, plus V tan delta. Delta is the friction, angular friction between the base of the foundation and the soil. So this one. So factor of safety against sliding is actually T by H. What is H? H is the horizontal component of P, that is P sine alpha. So now let us put all the value. So T, what is the area? Area is 2 into 3, so 6. And what is the value of CA? CA is 0.7 C. What is the value of C? 75. So 0.7 C, that means 0.7 into 75, plus what is the value of V? What is the value of V? V is this one, 3000 cos 10 P cos alpha, 3000 cos 10 degree. And what is the value of tan delta? What is the value of delta? Delta is 0.8 into 5. What is the value of 5? 25 degree. So 0.8 into 25 degree. So this one is the T. Now divide it by H. What is the value of H? H is P sine alpha. That means 3000 sine 10 degrees. If you solve this, you will get the factor of safety as 2.67, which is also greater than 1. That means the horizontal component of P, of load P, will not cause any sliding, since this is greater than 1. Have you all understood? If you have any doubt, you can tell me now. Does anybody have any doubt? Hello? Have you all understood this problem?
Yes, sir.
It's clear. You're audible. Thank you.
Okay. So,
Hello, sir.
yes, tell.
Actually, I don't have any doubt in this example, but I just wanted to ask that what is the difference between C and CU?
C and CU. There is a look. C can be CU is the unrent cohesion. It is determined in unrent condition. Suppose if you use that triaxial experiment in unrent condition, you will get the CU value.
Okay.
Okay. If you
Hmm.
plot the Mohr circle, after doing the undrained test, you will get CU value in undrained condition. There are two conditions, right? Drained and undrained. So
Hmm.
C value corresponding to undrained condition, you will get CU value.
Okay.
Okay.
Okay. Thank you.
Okay. Uh, so let us solve another problem, the last problem. So the problem is our 2.5 meter wide strip footing is placed at a depth of 1.5 meter. So it is also a strip footing. The breadth is 2.5 meter. Depth is 1.5 meter. The water table is at a great depth. Determine the percentage decrease in the ultimate capacity of the footing. When the determine the percentage decrease in the ultimate capacity of the same footing with a depth of 1.5 meter. The depth is 1.5 meter. When the water table rises up to a depth of 0.7 meter below the ground surface. Okay, so a 2.5 meter wide strip footing is placed at a depth of 1.5 meter. Strip footing of breadth B is at a depth of 1.5 meter. df is equal to 1.5 meter. Fine. When the water is at when the water table is at a great depth. So in the first case, the water table is at a great depth. So we need to determine the percentage decrease in the ultimate capacity of the same footing with depth of 1.5 meter when the water table rises up to a depth of 0.75 meter below the ground surface. So what is happening is that in first condition there is no water table. Means water table is is at a great depth. In the first condition, water table was very lower, is at a great depth. But in the second case, we can see the water table rises up to a depth of 0.75 below the ground surface. So this one is the first case. The water table is at a great depth. Suppose here, that is beyond B. Suppose up to this B, beyond B, the water table was beyond B, and after some years, suppose the water table rises up. So suppose water table is now over here. It is 0.75 below the ground surface. This one is the ground surface and water table is over here, 0.75 meter. Take gamma bulk equal to gamma set is equal to 17 kilonewton per meter cube, and the unit weight of water is 10, phi is 38 degrees, C is 0, this is a sandy soil, in Q is 60, in gamma is 75. So first of all, we need to determine the percentage decrease in ultimate capacity. Okay, so first of all, I need to determine the ultimate bearing capacity for this condition. After that, we need to determine the ultimate bearing capacity for this condition when the water table rose up over here and the water table is at a depth of 0.75 below the ground surface. And after that, we can find out the percentage change. Okay, so how we will do? In the first case, the water table was at a great depth, so there will be no effect of water table on the bearing capacity of footing, on the bearing capacity of the footing. Okay, so first case, dry case, on the soil in the dry case. So what was the formula for the ultimate bearing capacity for the sandy soil? So it is CNC plus QNQ plus half into gamma B in gamma. C is 0, that means C is 0, this is a sandy soil. So this part is 0. So Q in Q plus half into gamma B in gamma. So what is the surcharge, effective surcharge at depth df over here? In the dry case, we can see the gamma bulk equal to gamma set is 17. So the 17 into df. So Q means 17 unit weight into df. What is the value of df? The value of df is 1.5 meter. 1.5 meter. And what is the value of NQ? NQ is 60. plus half. And in this case there is no effect of water table, so we will use dry only. This bulk and saturated both are same, so we will use bulk because there will be no effect of water table since the water table is at a great depth beyond B. So 17 into breadth of the foundation. What is the breadth of the foundation? It is 2.5 meter wide. And what is n gamma? 75. N gamma is 75. Now if we solve this, we will get the value 3124 kilonewton per meter square. Now for the second case, when the water table is over here, 0.75 meter below the ground surface. Okay, so the below this, this part is totally submerged. So for this part, for the third part means for this part we need to use the submerged unit weight. For in case of when we are considering this, the submerged case. For the submerged case, QNU equal to Q U equal to Q into NQ plus half into gamma B N gamma. Okay. And now Q. What is the effective surcharge at depth df? What is the effective surcharge at depth df? In this case, it was just gamma into df. But now over here, you see, it will be the surcharge over here is gamma into this part, because this part 0.75 up to 0.75 depth it is dry. So gamma bulk into 0.75 plus this part is totally submerged. Okay, so gamma submerged into what is the depth of this part? The total depth df is 1.5 meter. So 1.5 meter, the total depth is 1.5 meter and this part is 0.75. So 1.5 minus 0.75. Okay, so this one is the value of Q for the second part, Q2. Okay, Q2. This one is suppose Q1. This one is Q2. So let me put all these things over here. So gamma bulk is 17. 17 into 0.75. I am putting the value of QU2. Oh, plus submerged. What is the saturated? Saturated is 17. So gamma sub means saturated minus unit weight of water. Saturated is 17. Unit weight of water, suppose it is, let's say, it is 10. Okay, let us consider 10 kilonewton per meter cube. So this one is 7. So 7 into 1.5 minus 0.75. So 7 into 1.5 minus 75, I guess it is how much? 0.75. So this one is Q2. And what is the value of NQ? NQ, the value of NQ is 60. So it is 60 plus this part. The third part, in this case, since this is totally submerged, this part is totally submerged. So for the third part, we will use submerged unit weight. So half into submerged is 7. What is the breadth of the foundation? It is 2.5. And what is the N gamma? What is the N gamma? N gamma is 75. 75. If we solve this, we will get the answer 1736 kilonewton per meter square. Okay, this one is the ultimate bearing capacity for the second part when the water table rose over here. Okay, in the first part the bearing capacity was this when the soil was completely dry, and when the water table rose, and when the water table rose over here, when the water table rose over here, the bearing capacity decreased because when the water table rose up, the soil which was over there, it softened. So naturally the bearing capacity decreased. So we need to determine how much percentage the bearing capacity decreased. So percentage decrease. So what is the percentage decrease? What was the original in the first condition? It was 3124 kilonewton per meter square. 3124 kilonewton per meter square. And what is the change? What is the second? What is this one? The final bearing capacity when the water table rose up. It is 1736. The present bearing capacity divided by original bearing capacity, which was earlier in dry condition. So if we solve this into 100 and also percentage, if we solve this, we will get 44.4%. This is the change in the bearing capacity. So that means 44% change is observed when the water table rose up from below the ground, so rose up to a depth of 7.75 below the ground surface. Okay, so if you have any doubt regarding this problem, please tell.
So please again explain the how we calculate the value of Q1 and Q2.
Okay. See, in the first case, you see in the first case, the water table was at a great depth. See, it is written over here. A 2.5 meter wide strip footing is placed at a depth of 1.5 meter when the water table is at a great depth. Okay, so in the first case, the water table was at a great depth. So what will be the value of QU at DF, at point DF? What will be the value? It is only DF into gamma, right?
Yeah.
So what is the gamma? Gamma bulk is 17. So 17 into DF is 1.5. So Q1. So what is Q1? Q1 is only gamma into DF. You see,
Yes,
gamma
sir.
into DF. Okay. So this one is Q1. But in the second case, the water table rose up. Water table is now over here, 0.75 meter below the ground surface. So what will be the Q2 at DF, at a depth DF, the effective surcharge? So this part, the part above the water table, is in dry condition or maybe partially saturated. For that I am using bulk. See, bulk into
Yes, sir.
0.75, and the rest part is completely saturated, submerged underwater. You see, completely submerged underwater. So for that case, I am using submerged emitter. So the depth of the foundation is 1.5, and the depth of the water table in the second case is 0.7 meter from the top. So if we subtract 1.5 from 7.5, we will get the depth of water table, right?
Yes, sir.
So if we multiply depth of water table with the submerged unit weight, and if we add gamma bulk and 0.75 for the upper part, we will get the value of Q2.
Yes, sir.
If you have any doubt, you can tell me. I can explain once again. So,
No, sir, it's clear now.
okay. Okay,
Thank you,
so
sir.
okay. So if you have any doubt regarding to this session, you may tell. If any of you have any doubts, you may tell now. You may write in the discussion box also in the NPTEL forum. If you have any doubt regarding to today's session, you may tell now. I have solved 7 problems. If you have any problem regarding these 7 problems, you may tell now. So you all have understood what I all the problems that I have solved today.
Yes, sir.
Okay then. Okay then. Thank you for today's session. Thank you for attending. And I will see you in the next week. Okay, next Tuesday. Okay.
Thank you, sir, for bringing us class.
Okay. Keep practicing. Okay.
Yes, sir.
Okay. Thank you.
Thank you very much, sir, for your
Okay.
valuable insightful session. Thank you so much.
Okay. Thank you so much. Thank you. Okay. Bye.